Welcome, colleagues, to those of you who are joining us online right now. I can see a few names coming into the Zoom space at the moment, and I'll keep monitoring this space. I'm monitoring. My name is Marcia Meskin, and I'm the director of the Institute of Advanced Studies, and it's my absolute pleasure to welcome you both online, but more importantly, an absolute full house here at International House, and this is fantastic. You are a very popular speaker, and we are very excited. So welcome, colleagues and colleagues. There will be lunch, so I also welcome you and ask you if you wish to join us after this talk for lunch. You are all more than welcome to stay. This is very, very delightful. For those who are joining online, I will be monitoring the Zoom the webinar format, Q&A and chat. So you are very, very welcome to feed conversation or questions in through the chat or through the Q&A throughout the talk today, because I know many people will probably want to ask questions, and we will make sure that those questions are brought into the final dialogue. All I want to say at this moment, as we're welcoming, is that I want to very much welcome José Ferreira Alves, Professor of Mathematics at the University of Porto. And we are really thrilled today by the title of your talk. I have to say, it's always wonderful to have a talk where there is both a very obvious and kind of disciplinary framework, but where you have, for example, something like your talk, where a humanistic concept like chaos might be discussed from the perspective of mathematics and science. So this is a really exciting and interesting dialogue for us here at the Institute. And I'm now going to turn over to my colleague, Professor Wael Bassoud, who is going to give a much more detailed introduction to José's work. But very much welcome from on behalf of the IAS, and we are very delighted that you've been spending this time with us.
Very much.
Thank you.
Very pleasure to be here.
Thank you, Marcia. So a brief introduction to Professor José Alves. José is a professor of mathematics at the University of Porto and the head of department currently. José obtained his PhD from Ponca in Rio de Janeiro in '97. This is one of the most famous institutes, in particular for dynamical systems. It produced the Fields medalist Arthur Avila. And José was supervised also by one of the most influential figures in dynamical systems, Marcelo Viana. From his PhD, he published his work in Annales Scientifiques de l'École Normale Supérieure, followed by a publication in Invenzioni Matematiche, which is the top journal in mathematics. That work formed a cornerstone in the field, in particular in the area of partially hyperbolic systems. José continued to publish at the highest level, including publications in Advances of Mathematics, Transactions of the American Mathematical Society, and the Journal of European Mathematical Society, and also supervised more than 9 students, PhD students, with 2 to come very soon. José likes Lapra a lot, and he visited the university several times, including a 10-month visit, which was supported by the Leverhulme Trust under the scheme Leverhulme Visiting Professorship. So far with José, we have 2 joint published papers. For the past month, we have been working on a project related to the famous Lorenz attractor, which is José going to tell us about in his presentation. Please, José.
Okay, thank you, Wael. Thank you for the invitation to be here. You have always been the one that invited me to come here since the very beginning. As you said, I like very much Lapra. Not only me, but also my family. I'm here with my family, and it's a great pleasure for us to be here. Thanks for this kind of introduction. Thanks to the Institute of Advanced Studies for supporting financially this visit. Thanks also for the very nice accommodation. We are very happy to be there. Very nice place. And thanks the audience for coming. See, I didn't know I was that popular. I'm gonna believe you come because of me, not because of the lunch. So I will talk about chaos and a probabilistic approach to chaos. That's the field I work. I work with chaotic dynamical systems, and I try to say something about chaotic dynamical systems from probabilistic point of view. And I think there's no better way to start than from the beginning. And this goes back to the work of the famous French mathematician, Henri Ponca. And one of the main problems, or the main phenomena we are going to discuss here, something to do with, it's very important in his mathematical production, and also in his life, financially speaking, I would say. And it has to do, well, it has to do with by the end of the 19th century, Mittag Leffler, a Swedish mathematician, designed a scientific competition in honor of the King Oscar II from Sweden, and to award the best work on 4 pre-assigned problems, important problems in mathematics. And Henri Poincaré addressed the important problem on the 3-body problem. The 2-body problem was already known. Well, the goal was the solar system, but after the two addressed the 3-body problem, and he won that competition. The work was very good, and so the prize was 2,500 Swedish kron, which presently is more or less like 180 pounds, which at that time was, I imagine, it was really something. Well, the work was accepted for publication. I think it was part of the prize to be accepted for publication in Acta Mathematica, which is until nowadays one of the best journals in mathematics. But there's a but. Fragment, a young mathematician, I think he was not a student of Mittag Leffler, but was working with Mittag Leffler. He had some doubts in the paper. I think Mittag Leffler gave that work of Poincaré for him to study, and there were some problems that he couldn't understand what was Poincaré saying. So he addressed, so he sent Poincaré some message pointing those specific problems. What happened is some months later, Poincaré sent a telegram to Mittag Leffler, said, there's a problem in my work, and I would like, so the work was already in print, in the journal, and I would like to buy the journals which are already printed, and actually he had to pay more than we got from the price. 1,000 more, which is about 70 pounds. So it was expensive, this experience for him. But the problem, it has to do with something we are going to consider here, is a phenomenon of sensitivity to initial conditions. I'll try to give you more precisely what this means, but he was not aware of this phenomenon. And what was the cause for that error in his work. Okay, so, but what is dynamical systems? So he was is considered the founder of this theory of dynamical systems. Let me tell you briefly what do we mean by dynamical systems. Well, essentially it's some system whose configuration changes over time. So as time evolves, the configuration is changing. So we all know a lot of systems like this, solar system, meteorology, is very important. Every day we see the forecast and it evolves, it changes the configuration. A population in a certain ecosystem, the number of individuals changes. The shares on the stock market. It will be very important to predict the evolution and to have money out of that. It's very difficult. So how do we work with this? So we have to model the problems, and that's one of we have to model the system, and that's one of the main problems, to find a good modelation of the system. For that, we essentially need two things: the phase space, so where the space of configurations, and the evolution law. Okay, we need to know what are the configurations, which phase they are, and the law that tells us how that will evolve in time. And the goal is to predict, to know what happens in the future. Okay, so these are the objects and the goal. Well, and here we are going to consider these two types of systems. There are more approaches to these problems, to this modulation, but essentially in the field I work, we deal with two types of systems: continuous and discrete time. So it has to do with time. So time can be continuous or discrete. In continuous time systems, we have the vector fields and the flows that come after those vector fields. Essentially, so we have a space where it's going to evolve, and we have a vector field which at a point in that space gives us the tendency of evolution. And we have a differential equation for those who know what it is, and we integrate the differential equation and we find the trajectories of points. So at a certain point, we have the tendency, which is that vector x prime, which depends on the point. So that's why I put f of x, it depends on the point. And we have trajectories which are tangent to that vector field. So this is the continuous time systems. And we have the discrete time systems, which essentially are defined by a function from a space into itself. Okay, so with the function, we pick a point, that space, x, and we see the image by that function. We have f of x, and we see the image of the image that we denote by x squared. X squared is not the power, is not multiplication of numbers, it's image of the image, okay? F cubed, which is the image of the image of the image. So we have these compositions, which is calculated in successive images that we denote by Fn, and for 0 is the identity. So x is equal to f0 of x. Okay, so what is the orbit in this case? So in the other case, the orbit is the trajectory. Here, the orbit is the sequence of images of that point. Okay, and we say that the orbit is periodic if there is a certain iterate after which it comes to itself. In this case, of period t. Okay, some simple examples of continuous time systems. For instance, if I give you the vector field at a certain point, xy, as being the vector itself, so at a certain point here, this point has two negative coordinates, all both equal, so the vector is itself, so it's pointing in this direction. Okay, so this is the vector field. Okay, we plot at every point. Here is not every point, but in a large number of points, we plot the vectors, and it's not difficult to guess what will be the evolution of this system, the trajectories. Well, it's semi-lines coming from the origin going to infinity. Okay, straight lines. Okay, this is the trajectory. If you take a point here, the tendency is to come here. But we can guess looking at it. We don't need to integrate. Of course, in this case, we can integrate and have explicitly the trajectories. But one of the goals of this theory, well, it has to do with the difficulties of differential equations. We know certain types of differential equations that we can integrate, but it's very easy to give you a simple example of a differential equation that I will present here in 2 minutes that we cannot integrate. So we try to say something about that system, even if you cannot apply the classical theory of differential equations. Okay, looking at this, we don't need to integrate to guess what is the tendency of the orbit. So it's going to infinity coming from 0. If we reverse signs in the vector field, it's easy to see that we come from infinity and we go to 0. So all trajectories will die in point 0. 0 will be an attractor. It's attracting, a very simple one, but it's attracting all trajectories. And there are other cases. So switching the coordinates y and x will take this trajectory kind of parabola with the degenerate cases, which are here these lines. Okay, so trajectories here, we can look at that and we see, well, most of them will be parabola with the degenerate cases. And this one is minus yx. Well, it's orthogonal to the
position. So the trajectory will be circles. Okay. So this is to say that, well, first of all, we have examples where we can plot the vector fields, and without knowing, I imagine that even those who don't know what is a differential equation, it's not difficult to guess what will be the tendency of the trajectories here. Okay. So simple examples. But unfortunately, not all cases are like this. Not all, as I said, not all vector fields can be integrated. And in particular, this equation, the famous equation by Lorenz. So Lorenz is an American meteorologist. In 1963, he presented a three-dimensional vector field. So the vector fields I had before were two-dimensional space, in the plane space. Now it's three-dimensional. He presented that as a simplified model for the atmospheric convection. So that tendency of the hot air to go up and the cool air come down. So that creates these masses of air, and that's what influences the meteorology, so the weather, and trying to predict that. He simplified, not our three-dimensional space, but with a model in a two-dimensional space. Sorry, he's modeling three-dimensional space, but to model, because there are more variables, and I'll let you know what are the variables. So it's three-dimensional, the model, but to model a phenomenon in two-dimensional space, okay? So the space is three-dimensional, so with three coordinates, here is x, y, and z. And the evolution law is this one. Well, look at it, well, it's not integrable. The problem, if it were linear, if there were no terms multiplying the variables, it would be integrable. But there are, if you look at the expression, there is xz and xy, that's the problem. So it's not linear, and we cannot integrate. There's no theory that can be applied to this differential system of differential equations. So let's try to say something about this without the theory of differential equations. Well, just to let you know, it's not important, but just to let you know that x is the convection rate, y and z are in fact the variation of temperature in the horizontal and vertical direction, and sigma, r, and b are constants, physical constants. Just keep in mind that r is 28 in the study of Lorenz. There was some motivation for this constant. R is 28 in the Lorenz study, and sigma 10 and b equal to 8/3. Okay, so he made some experiments and some calculations and realized that there was an attractor. What do I mean by an attractor? There was some box that he started with some initial condition. He programmed a computer to see what is the, even not being, we're not able, as I said, to integrate the differential equation, but we can do numerical simulation, get good approximations of the orbit. And he realized that no matter inside a certain box, no matter the condition he took, in the future it came to something with this shape, this kind of butterfly. And and he realized that there was an attractor, so no matter what was the initial condition, the orbits go there, so attracting, and with a somewhat complicated structure, fractal structure. I'm not going to fractals, but there's a lot of theory about fractals, and this is a good example of a fractal. And you realize it displayed that problem of Ponca, the sensitivity to initial conditions. And that's our next goal. What is the sensitivity to initial conditions? Well, so in numerical simulations, he looked at, this is a plot for the x coordinate. And he did some numerical simulation. He had a big data of numbers. And at a certain moment, it stopped one day. And the next day, so it had more numbers, but it came to a number in the middle, one of the data that he obtained. And it truncated from 6 to 3 decimal places. And it made the computer that routine for producing the numbers again, continuing. And he realized that, well, in the beginning, essentially, he obtained what he had in the previous day. But after a while, not a long time, he realized that it was, well, it's not exactly what I was expecting. I made some, I rounded from 6 to 3. I was expecting something which stayed close to what I had in the previous day, and it was not. Well, he even considered the possibility of failing the hardware. By the way, it was a computer, a big computer with 16 kilobytes. Something 1/10 of a bad picture that we take today with cell phone. But it was a great computer for that time. Well, but it's at this point, it may be good to recall that 1 century earlier, Maxwell had warned that the postulate of determinism, the same causes produce the same effect, should not be confused with similar causes produce similar effects. And this was the point. Okay, he was expecting similar effects from similar causes. And already 1 century before, Maxwell was warning about that problem. Well, in fact, some years later, so in 72, Lorenz wrote that famous article with this title, Predictability, does the flap of a butterfly's wings in Brazil set off a tornado in Texas? And this is where the butterfly effect comes, and many people refer to it. So it has to do with this, a small perturbation producing a big change in the evolution of the system. Okay, so let me say even more about this. So this is the sensitivity. So that's the idea. I will show you more precisely, in more precise mathematical terms, the appearance of this phenomenon. But this is the idea. So small perturbation, big change in the evolution. I will refer to it in short as FIC. So it's important in this attractor, it has a singularity, this attractor. There was, in the 60s, it was developed a very important theory by Smale in Berkeley and many of his students, also in Russia, Russian school, well, Soviet Union at that time, the Soviet school in parallel. They didn't interact. At that time there was a wall, but Smale went to Russia and they started to interact even that time. And there was this theory of hyperbolic systems, I'll mention it in the end. But they didn't, those hyperbolic systems, which were connoted as the stable ones, robust, they didn't have singularities. So that was not present in those systems. This Lorenz attractor has a singularity. So what is a singularity? It's a point where the vector field is zero. So the tendency of motion is zero. So there's no motion. So it's fixed. So it corresponds to a trajectory which is constant. In this case, it's very easy to see that you replacing that expression x, y, and z by zero, you obtain the x prime, y prime, z prime equal to zero. So that's a fixed point, is the singularity of this system. And for r bigger than 1, see that Lorenz considered r equal to 28, so that's the case, much bigger than 1. With the derivative, well, this is somewhat technical, but for those who don't know, don't be scared. Derivative gives information. So derivative is the usual derivative that people, I think in Portugal at least we learn in high school. This is derivative with several variables, but it also has the flavor. It's a good approximation of the system. And there's a notion of eigenvalues which give information, qualitative information on the system. And it has 2 negative eigenvalues, the derivative, and 1 positive eigenvalues. The fact that it has two negative eigenvalues implies that there is, through that, so we have I'm not going to point because people at home won't see, but the fact that the singularity has 2 negative eigenvalues makes that there is a surface passing through the singularity, so something 2-dimensional, made of orbits which converge to the singularity in the future. So that's why we call it stable. It's stable because it's attracted by the singularity. And because there is one eigenvalue, lambda 3 in the case, bigger than 0, there is a 1-dimensional manifold that we call the unstable manifold of orbits which go away from the singularity. That's what I call here gamma minus and gamma plus. Here are two, one on each side of that surface. Okay, so we have a two-dimensional stable manifold and a one-dimensional unstable manifold through the singularity. With this, we understand locally very well the behavior. If you are on those manifolds, completely understood what's the behavior. If you are not, if you are close to the stable manifold, the tendency is to go down, but also there's a coordinate pointing out, the coordinates related to the unstable pointing out. So it becomes, it's a kind of parabola. Okay, so that's the tendency of the other orbits. So what those orbits in the stable manifold, they go to the singularity. Those on the unstable go away from the singularity, and the others do something like a parabola. I said parabola, a parabola. So like this. Okay, as in one of the cases we have seen two dimension. Okay, so we have an understanding of the local behavior at the singularity, but the attractor is much more complicated than just the singularity. And it's so complicated that in the late 70s, Guckenheimer and William tried to simplify that model. Well, that's something that we do frequently in mathematics. We have something very complicated. Let's pick some simplified version of that, reasonable, of course, has to do something, has to have some of the flavors that the original problem we have. Let's try to understand this one. If we don't succeed, why are we going to try the other one, which is even more complicated? So they presented a simplified version. That's known nowadays as the geometric model of the Lorenz attractor, also known as the geometric Lorenz attractor. And they did, essentially, they know what is the local behavior at the singularity, and they completed the picture. So they put some, that's what we call a section that they call sigma, is that square there, made of two rectangles, gray and red or pink, something like that. So that's that square. So the tendency, if you believe in what I said before, the tendency in this rectangle in red is of orbits starting there is to go down, but go away from the stable manifold because of the component in the unstable direction. So after a certain time, the points that are, there is a line separating these two rectangles of points which go to the singularity. So they don't come here to this triangle here on the right, but all other points on this red rectangle, they come to this triangle on the right. Okay, the points in the line that divides the two, they go away, so they don't come here. Okay, and the same happens on the other side, they go to the other side. And what Guckenheimer and Williams they proposed was, let's complete the picture. And since we have a tendency of contracting one direction, expand it up, so the picture was completed in this way. So this triangle goes there and touches the vertex here, touches there, and the other part comes like this. And symmetry on the other side. And so this is, that's what they call the geometric model. Of course, they studied the Lorenz attractor, and they realized that it was something like this. This captures the flavor of the Lorenz attractor. And well, for this, there is a transformation. So we have sigma, okay, this square. There's this line which I call gamma. It's already mentioned here in the picture, of points that go away. So I don't expect, if I take a point there, that it comes back to sigma. But all other points, by the construction, they come back to sigma. So we have a dynamical system. So a transformation from a space into itself. Well, let's forget that gamma. Or if you want to complete it, saying that gamma, they come all to gamma again, so no problem. Okay, so we can think of it as a transformation from a space into itself. I'm going to study this from a probabilistic point of view that gamma is not important because it has zero measure. Essentially, for those who know what are these words, that's the reason. Okay, so we have this, that's what we call a Ponca map, because Ponca already considered this situation. So considering a flow and some section transversal to the flows in such a way that when orbits come, they pass and they go to the other side. And coming back here, we have a transformation. And that's what we call nowadays the Poincare transformation. Well, since the appearance of this model, many works have been published about this geometric model. a lot of works, scientific works, accepted in journals, very good ones. Well, but at this point, does it have, so do the Lorenz equations in the model considered by Lorenz are actually, they are actually described by this geometric model? That's a natural problem. I said it has the flavor, but is it really like this? Well, this actually was posed as one of the problems of the 18th problem. So Smale is one of the great mathematicians alive, the one that in Berkeley developed this theory in the 60s and 70s. And it was asked to elaborate a list of problems for, by the end of the previous century, a list of problems for the next century, our century now. And he presented 18 problems, and this was one of them. To his bad luck, it was solved in 1999, before the end of the century. It was solved by Warwick Tucker, a Swedish mathematician, now working in Australia. By the way, a student of Carlson, the great analyst, works in analysis, one of the great mathematicians. And the proof was somewhat polemic in the beginning because it's computer assisted. Created some routines for the computer to check, and that makes mathematician. But it was accepted. So it's proved that if we study the geometric model, we are actually studying the Lorenz system. Okay. So let's try to say something about the geometric model, since we have this nice result by time. So this is the transformation, the Poincaré transformation that I described before in the geometric model. So it's like this. So this Poincaré transformation, it contracts in the vertical direction, and it expands with, of course, with a discontinuity in the horizontal direction. So the dynamics, the evolution in the vertical direction is not so interesting. So the tendency is if you pick two points in the same line, they will approach in the future. The important, interesting part of the dynamics is in the horizontal one. So that's what we do frequently in mathematics, is quotienting. Let's forget the vertical, think only of this transformation in terms of the line. So think of each line as a point. And what we have, so we have a one-dimensional map now, which is like this. Okay, so this is what we call the Lorenz map. So Lorenz flow, Poincaré transformation. So Lorenz flow in 3 dimensions. Poincaré map in dimension 2. And now the Lorenz map is the quotient of the Poincaré in dimension 1. So we have this relation from the flow, we go to the Poincaré map to the quotient map. It's very easy to see, just think a bit, and you'll see that if you have a periodic coordinate for the quotient map, well, think a bit, passing from the point of the quotient map to the Poincaré map, you have to know a bit more of mathematics. But what does it say? It's a periodic coordinate. Well, it says that when you go to the Poincaré map, we have a periodic line, a line that goes away and it comes back to itself. But comes back each time we iterate, it's contracting in the horizontal, in the vertical direction. So when it comes back to itself, it comes strictly inside itself. And there is this nice theorem about the existence of fixed points for maps of an interval into itself. It's consequence of the Bolzano. In Portugal, we know that Bolzano theorem. So a transformation of an interval into itself, continuous transformation, interval into itself, must have a fixed point. So a fixed point, so we have a fixed line with a fixed point in that line. Well, it's a fixed, so it's a fixed point for that transformation, but it was taking several iterations to come back. So it's a periodic point. So that's why from a periodic point there, we have a periodic point here. And now just think of the nature of this Poincaré map is going, so it's going down and coming back. If you close this line, you have a periodic coordinate. Well, so maybe you have to come back several times, but when you close, you have a periodic coordinate for the initial flow. Okay, so there's information. This is to say that from information of this one-dimensional map, see that it's much simplified. So we started with a three-dimensional flow, very complicated. Then we went to the Ponca map, and now we are deducing information for the original system from this one-dimensional map. And it's also not difficult, but I won't do that hand waving. It's not difficult to see that we have sensitivity to initial conditions on this one-dimensional map, essentially because the derivative is bigger than 1. It's expanding in that direction. That makes that Ponca map also has sensitivity to initial conditions. So 2 points have a tendency to separate. And that makes also sensitivity to initial conditions for the Lorenz law. And there is also a way of passing something that I still haven't introduced you to this object, but that's my goal in the next slides, is to introduce these physical measures. That's precisely our probabilistic approach to this kind of systems. So if we have a physical measure, it's true, it's of course not hand waving, but it's not that difficult as well. We have a physical measure for the quotient map, for this one-dimensional map. Then we'll have a physical measure for the Ponca map, and we'll have a physical measure for the original system. If these physical measures are good, that's great. You can say something about this. And that's what I'll try to convince you, that these physical measures are good. Also introduce you to in a simple way. And the best way of introducing something is with toy models, that simplification, that keeping some flavor of the original problem. So Lorenz map is not exactly like this, but that's not that different from this. Okay, there's some differences, but not that much. So if we understand this, maybe we are on the way to understand something about the Lorenz map. And this is the graph let's think of. So we have an interval on the graph of this transformation from 0, 1 to itself is, well, that expression 2x mod 1 means multiply by 2 and remove the integer part. If it's bigger than 1, you remove 1. So when you are from 0 to 1/2, you are exactly multiplying by 2. And so you have there the plot of the graph of 2x. But once you go beyond 1/2, it will be bigger than 1. And so you have to remove the integer part. And so you repeat that straight line on the right-hand side. Okay. So let's understand in symbolic terms the dynamics of this transformation. It will be very useful for what comes next. So we can think of a point in its decimal expansion, 0, comma, blah, 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 or point, blah, 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 symbols from 0 to 9. But you can also define or describe points. You don't need 10 symbols. We do it more convenient, we have 10 fingers, maybe it's better. But it's enough 2 symbols. Okay? If you say the first symbol, so the 2 symbols, well, the 10 symbols are from 0, 10 digits from 0 to 9. That's the usual that we deal with. But you can use only 2 symbols. It's enough for describing a point in 0, 1. The 0 and 1. And with any number of symbols you can describe. So that's what we call base 2. So base 2, because this is the way computers work, with the less number of symbols, better. So for instance, if it has in A1 position, the symbol 0 means it is in the first interval, 0, 1/2. If it has the symbol 1, then it is in the second interval from 1/2 to 1. Then go to the second symbol, depending on whether it is the left interval or the second one, then you divide again by 2. And so you are approaching the number you give, and you can describe it precisely by that infinite sequence of symbols, zeros or ones. Okay? But this is very convenient for this dynamical system. Why? Because if we have a point described by this infinite sequence of symbols, A1, A2, A3, and so on, the image of it will be precisely removing the first symbol. Think of this instead of having, maybe it's somewhat difficult for some of you which are not used to this. Think that you have multiplication by 10. Of course, the graph will be 10 lines like this. When you multiply by 10, what happens? The comma goes here. Okay? If you remove the integer part, what we have? 0, comma, A2, blah, blah. So here is the same. Not with 10, with 2. It's the same logic, the same mathematics behind. Okay? So very easy to understand this system from this symbolic point of view. Well, properties, some properties. It has a dense orbit. What do I mean by a dense orbit? Some point that you pick you start iterating it, and it goes close to any other point that you give. In the future, in a certain moment, of course, it may take a lot of time to get there, but it goes close to any other point. Well, I give, for example, it's not just one point that has a lot of orbits with dense orbit, but this one is very easy to describe. You put all possible blocks. Well, I start with blocks of length 1, which are 0 and 1. It's the only possibilities. Then I put blocks of length 2, which are 0, 0, 0, 1, 1, 0, 1, 1. Then of length 3, create this number. Okay. When you iterate, so you give any other point. So you give the proximity you want. So you fix a certain number of binary. That is not decimal, it's binary places. Binary. Okay. You fix a certain number of binary places. In this point, you have that sequence. Okay. It's a certain fix the length. You have that sequence. You iterate until that sequence is in the beginning, and so it will be close to that point up to that level that you. So this is a dense orbit. And also density of periodic points. It's very easy to see that we have fixed points of points of period 1 at the distance at most one half. See that 0 fixed point, and well, technically, forget this. So think that it's continuous because technically it's 0 image of 1. It's 1. Okay, it's just this is just for short notation. Okay, if 1 is fixed as well, okay? And so any point is at the distance 1/2. Then if you plot the graph of F2, it's precisely 4 things with a bigger slope like that. You divide it into 4, so the intervals you plot like that is easy to see. Well, for obtaining the fixed points, you put the diagonal, and it's the intersection of the diagonal with the graph. When you want the period 2 points, you plot the graph, you put the diagonal, and on each interval of length 1/4, you find the line, the diagonal across the graph. So we have a point of period 2. And so that's the way we obtain density of periodic points. And also sensitivity to initial conditions. Because arbitrarily close to any point, there is, so this is the precise definition of sensitivity condition, sensitivity to the initial conditions in this case. So at any, so we give any point, and we have, so there is a certain constant such that given any point, there is arbitrarily close to it another point whose iterates at a certain moment are away that constant that we pre-assign. The constant here is 1/2. Okay, so I give any point, and I'm gonna find x. I'm going to find a y such that at a certain moment, a certain iterate, they are at least 1/2 apart. Well, so as I said, given x, I can describe it by the sequence, and I choose y by switching the digit an. So with n a large enough position. So if n is large enough, the y and the x are close because have a lot of places and I'm shading in an, which is very far from the beginning. Okay, so they are close. So I can choose arbitrarily large the n, so arbitrarily close to the initial point. And so that's I underline the fact that it's arbitrarily large or large enough position means close enough. Okay. So what I mean is you go there and you an I replace by an prime. Switching is 0 and 1. So if an is 1, then an prime is 0 and vice versa. So this is the expression. Okay. So what happens when we iterate now n minus 1 times? Well, in the beginning will be precisely the position, the digit an, which in this case 1 is 0 and the other one is 1/2. Okay. So the distance between these 2 points, sorry, one is 0 and the other one is 1. Okay, so the distance between these 2 points will be at least 1/2. And so that's the way we prove, and I think it becomes more precise, the definition of sensitivity to initial conditions. We prove it in a system which is not exactly the Lorenz map, but is related to it, it's the flavor of the Lorenz map. So in short, this system, this orbit, density of periodic points, sensitivity to initial conditions, that what was called by some authors, in particular by Devaney, the famous book on one-dimensional dynamical system, introduce this as a definition of chaos. Okay. Well, this seems too bad. Well, there's no prediction, especially with this sensitivity to initial conditions. A little mistake in the future completely different behavior. So is there anything that we can say for this kind of systems with this bad property of sensitivity to initial condition? And this is where the probabilistic part appears. I will try to convince you that there are good measures, the physical measures for the system, this toy model, the 2x mod 1. And I go back to a result of Borel, French mathematician, that says that almost all numbers are normal. This for non-mathematicians might seem quite strange. It looks more like something from psychology rather than mathematics. What is being normal? Almost, but mathematics is not everything very precise. What is almost? What is being normal? Let me explain what it is. So almost all means except possibly a subset with zero, in this case, length measure. So we are in the interval. We have a notion of measure, which is length. I give you an interval, we know the length. Okay. So for those who don't know what is zero measure, well, you have a certain subset of the interval 0, 1. You can cover that subset by intervals. So the subset is contained in a union of intervals whose sum of the lengths, that's what we have there, that sum, that symbol, that sigma, the sum of the lengths is as small as we want. Okay. So this is our definition of zero Lebesgue. It's actually Lebesgue measure, length measure. What is normal? Well, written in any base. So here we are, as I said before, we are considered base 2, but the result, the definition is for any base 2, base 10, base 3, base, any base. All blocks of digits with the same length. So we have considered blocks of length 1, length 2, all blocks, so of length 2, we have 4. All blocks in almost every number appear with the same frequency. Well, blocks of length 2. If we have 4, the frequency needs to be 1/4. Okay, that's the frequency that appears in the infinite expansion. Okay, maybe for understanding better this notion is giving you some numbers which are not normal. For instance, the first one is 0, 0, 0, which the digit 1 does not appear. So the frequency of zeros is 1. The frequency of ones is 0. No, normal, not normal. That in parentheses for you not to think those who know what is being countable. We cannot count. I cannot give you a list, say this is the first and second, and I'll exhaustively present all. No, that's what we mean by uncountably many. Okay, so these are examples just. So translating normality, I need to translate to do some mathematics. Well, so we have this is the binary expansion, okay? The frequency of B is precisely this. So we go to a large number n, you count the number of times is equal to B. B can be 0 or 1, okay? And so being normal means that the frequency is 1/2. So here we have a block of length 1, okay? Well, now let's go back to the doubling map. So that was the concept, the explanation of the Borel theorem. Well, here we know very well this dynamics. If we have a certain B at the jth position, when we iterate j minus 1 times, will be exactly in the interval. So I have two intervals, I0 and I1, in the interval labeled by that B. So it has to do with the considerations I made before. So saying a number as in the jth position, the digit B, it means that when you iterate j minus 1 times, it will be either on the left interval or the right interval divided by 1/2. Hence, since this is equal to say this. So, but what is this in terms of the right-hand side of this last expression in terms of dynamics? Well, I'm counting the number of times the orbit of the point X landed in the interval IB. Okay? So if the initial condition X is a normal number, then we know that the asymptotic frequency, that's what it means, converted to 1/2, which is precisely the length of the interval. It says that for almost every point, the frequency of visits to the interval, either I0 or I1, is precisely equal to the length of that interval. Well, we can do the same considerations now with interval with the blocks of length 2, and we arrive exactly to the same conclusion, okay? Using the fact that almost every number is normal. And in fact, we can say that because every interval, now every subinterval 0,1 can be written as a disjoint union of intervals of this type. So we have what we call the dyadic intervals. They are special, but any other interval can be written as a disjoint union of intervals like this. So in this way, we can easily get that for this toy model, the 2x mod 1, given any subinterval of 0,1, we have that the frequency of visits of almost every point. So for almost all initial conditions, the frequency of visits is precisely the length of the interval. So see, we have a chaotic system with a lot of bad properties in a certain sense, but we can describe in statistical terms very well the orbit of almost every point. So we say that the length measure in this case is the physical measure of length. Because it describes, call it physical measure, because it describes the statistics of almost every point in the phase space. Okay? Well, that's the explanation. Okay, well, Lorenz map was not like the toy model. We actually have a theory for piecewise expanding maps. They're piecewise, if you can decompose the phase space into, it can be countably many intervals. It doesn't need to be a finite number, but in the case of Lorenz, it's just 2. And one of the key properties is expansion. So the derivative is bigger than 1. So lambda is bigger than 1. And depending on the type of system we are considering, there can be some, we need, just this is not enough to conclude that there exists physical measure for the system, but we need some extra conditions, which some of them say, for instance, is nearly horizontal. Doesn't need to be, horizontal, nearly a straight line. Can have some slope varying a bit, but not much. But there are also some other geometric properties or analytical properties. Lorenz map is an example of this. And there is nice result, actually 2 nice results. The first one by Lassot and York from 73, which says that if you have a piecewise expanding map like the ones I've described with these properties, then the orbits of almost all initial state is described by, not necessarily by 1. That's why I make this picture of this. If we start on the right-hand side, we don't go to the left. There's no interaction between the 2 sides of the vertical line. So it's not expectable that we have just 1 physical measure. In this case, for instance, at least 2. Okay, so this is to say that it cannot be described in general by just 1. But in the case of Lorenz map, is just 1. So how do we? This is, if you know probability theory, I would say simply there is a probability measure on the Borel sets for which this happens, and this is the probability measure. But for those who don't know and at least know what is an integral, there is a function. Non-negative function whose integral is 1. So this is probability 1 for the full space, because we are integrating the full space, and such that this holds. Okay, so this is the definition of the measure. In the case of length, the phi i's are precisely constant. Okay, equal to 1. Okay, so these are actually, for those who know what measure theory is, the measures are absolutely continuous with respect to the length. Okay, so we have these nice results. And why do I present this to? Well, first, Lassot York, because it was the first one in this direction, big result in this direction. Keller, because unfortunately Lassot York cannot be applied to the Lorenz map. Keller had to make some improvements for applying to that map. And that's why I quote also Keller. So this new one up to me are physical measures. Well, then a new phenomenon also present in these Lorenz equations. Mandeville and Pommeau, they detected that for large, see that Lorenz studied for R equal to 28. So for large, much bigger than the 28. There was a phenomenon of intermittency. I'm not going to explain you what is intermittency, but I'm going to give you a mathematical model for intermittency. Well, it's essentially, I have here so we take a number bigger than 0, which I call alpha, and see that the lower expression for x between 1/2 and 1 is 2x minus 1. It's precisely the right-hand side is precisely the graph of 2x mod 1. On the left-hand side, this is so the expression above is essentially changing a bit so here I have the plot of 2x mod 1. I'm changing to make it tangent at the fixed point 0. That's the change, okay? So this is the expression. Okay, so this is 2x. So this mapping, it has, from a topological point of view, it has properties similar to 2x mod 1. It has denseness of an orbit which is dense, denseness of periodic points. It also has sensitivity to initial conditions. But what about physical measure? Well, we cannot apply Lazotta-York nor Keller because it's not an expansive map, not a piecewise expansive map. Because one of the conditions, and the one that I stressed, the other ones said there are more conditions, is derivative being bigger than 1. Derivative, all points. Derivative here at 0 is 1. The expression go there is 1. So it's not piecewise expanded. We cannot apply Lazotta-York or Keller theorems. Okay? Actually, we can consider induce. So this is the inducing scheme. It's pretty close to the work on things I work. So we can consider on the right-hand side from 1/2 to 1 a partition into sub-intervals such that they return. So I'm just considering now from 1/2 to 1. I have a first interval which I call I1, such that if you consider that I1 on the first iterate, the points that start from I1 they fall into 0, 1 on to 1/2 1. And then there is a second interval, which I call I2, that they go out because the image is down, but in the second iterate, they come back. Okay, just looking there and we see that. A third interval. So we introduce this sequence. So we have that partition of 1/2 1 into intervals whose union is the 1/2 1, and the respective return times. So for the first one, I return in time 1, second one in time 2, and so on. We can induce a new map. So look there, I'm plotting that in red. So this is the graph of this function here, okay? Well, and this one is piecewise expanding. It's not difficult to see derivative is always bigger than 1. And there's a very nice result by Yang from 98, actually with another one in 99, which is closer to this one, but the first one in this direction is from 98, very famous, which says, if we have an induced map, so we have an original system F, little f, which is our intermittent map here in application, if it induces a piecewise expanding map. So if the inducing time is integrable, and it means essentially that the points of that return after much time, the measure is going to 0 in a somewhat fast way. So if the return time is integrable, then the original system has a physical measure. And more, this is the most important contribution of Yang, that the decay, so the measure of this set of points whose return is very big, bigger than a certain n, the way it decays, depending on n, gives information on mixing rates of the system. If this decays exponentially fast, then the system mixes. I don't go into that, but mixes exponentially fast. For the intermittent map, we have that it's integrable only when alpha is in between, so alpha is bigger. So alpha being bigger than 1 means the tangency at 0 is very big. Actually, you can prove that if alpha is greater or equal to 1, there's no physical measure for this system. Okay, so just two final slides. The construction of going back to the Lorenz attractor, the construction of the geometric Lorenz attractor gives, in fact, not just one system, gives an open set of systems. So we have many systems. So the geometry is stable in some sense, okay? And actually, you can think of it as a family parameterized by a certain parameter, which I call lambda, ranging in a certain metric space. And each x lambda is one of these Lorenz systems, has a unique, so we have seen that the Lorenz map has a unique physical measure that passes to the flow, and so has a unique physical measure. So a problem, does it depend continuously on the system? Well, the answer is yes. And this is a result by myself and a student of mine, Mohammed Sufi. We have proved that if you think of that family of geometric Lorenz attractors, you change a bit the system, the measures depend, of course, we have to introduce some notion of continuity of measures, but there are many notions possible. So they depend continuously on the system. Well, and just to finish, Lorenz equations highlighted the fact that we can have robust properties out of the world that was known as being robust in the 60s and 70s. In the school of Smell, for instance, they produced a lot of results. And it was not expected that systems with singularity would be robust in a certain sense. So that prompted the quest for extension of this notion of uniform hyperbolicity, the classical theory, to some other notion. And the notion was this one. Well, not exactly, but so there was a result. There is a result by Morales, Pacifico, and Pujals, which proved that a robust attractor of a three-dimensional flow containing some equilibrium must be singular hyperbolic. And what is being singular hyperbolic? Well, is essentially having a splitting of the tangent bundle, so directions with certain favor, one-dimensional contracting, and a two-dimensional not expanding. So if I put it here uniformly expanding, it would be the classical theory, okay? Expanding only in volume. So that can be one contracting direction in this ECU. But the fact is that the expanding, there must be another one that compensates that. The product of them, the eigenvalues, must be bigger than one. Okay, so they came to this theory. And there's, for instance, it appeared this book by Pacifico, the same, with Araújo, a very nice book where they present an exhaustive presentation of this kind of system. And just to finish, naturally, are there physical measures for these systems? The answer is yes. Actually, the strategy I used with Sophie for the Lorenz attractor, we can, with no much more new ingredients, essentially the same ingredients, prove that these measures also depend continuously when we have them. But we aim for more. We aim to obtain quantitative, not only continuity. Continuity is something, okay, it doesn't change dramatically, but if you control the perturbation, can you have a control on the measures, the proximity of the measure, effective? So that's what I mean by quantitative. For instance, Holder continuity or linear response, which means differentiability of the measures with respect to the system. Also address other types of perturbation. So I mean perturbing the system, but we can perturb in many ways, random. Actually, presently, I'm working with YL so this is work in progress with YL, so these are our goals for the near future. I'm considering impulsive perturbations in a certain region, as if there is an external force that makes some jump there. What happens for this kind of system? Okay, thank you very much. This is